Hi there! Welcome to the 5th episode of the Digital Electronics Fundamentals series. In the next few episodes we will talk about flip-flops and other interesting circuits that can be built with them. But to test those circuits we will need to input logical signals in them, and the easiest way to do so is to have a logic generator, a device that is capable of generating automatically such signals. Logic generators can be at times very expensive, depending on their features, but a simple version of logic generator can be made at home very cheaply, and it is enough for learning the basics of digital circuits. And that's why today we are going to spend some time building such a device. Let's begin! Before entering in the details of the logic generator schematic, I need to tell you what a Schmidt trigger inverter is. Here is the datasheet of the TTL version of it, and of course there is a corresponding CMOS version, which we will not take care of it right now. The IC contains 6 of this kind of gates and is available in several formats. The one we will use is the one with a PDIP socket with 14 pins in 2 parallel rows of 7. The Schmidt trigger inverter has the same symbol of the regular inverter, but inside the symbol itself there is a picture that identifies it as a Schmidt trigger. The peculiarity of such a device is its capability of modifying an irregular input signal into a perfect TTL signal. It does that using at its input a voltage comparator that has 2 separate thresholds, usually named Vt plus and Vt minus, where Vt plus is greater than Vt minus. When the input signal becomes greater than Vt plus, the output of the device becomes a 0, and when the input signal becomes smaller than Vt minus, the output of the device becomes a 1. These images on the right side describe very well the behavior of this device. In figure 31, for example, you can see the correlation between a periodic input signal, irregular in shape, and the output, which resembles a perfect periodic pulse signal. See, when the input signal is low, the output is high, and later only when the input signal exceeds Vt+, the output goes low. And then only when the input goes below Vt-, the output goes high again. We will use this property to straighten up the signal obtained from charging and discharging a capacitor to make it become a nice periodic pulse signal. Let's see how we can do that looking at the schematic. Let's concentrate first to the leftmost part of it. We have a Schmidt trigger inverter, a capacitor, and a resistor in series with a potentiometer that creates a sort of feedback between input and output of the inverter. Let's assume, for a moment, that the capacitor is totally discharged. In such condition, the voltage at the capacitor is 0, and therefore, because it is lower than Vt-, the output of the inverter is high. But, because the output of the inverter is high, there will be a current going from the output, through the resistors, into the capacitor, which will start charging it according to the time constant Rc. While the capacitor charges, its voltage will begin to increase, and as soon as it reaches the value of Vt+, it will cause the output of the inverter to go low. Now that the output is low, the flow of current in the capacitor changes direction, and the capacitor begins to discharge through the resistor and the potentiometer. And so now the voltage of the capacitor decreases, until it reaches Vt-, and at that point the inverter switches again, the output goes high, and the cycle begins all over again. You see what we have? Yes, an oscillator that provides a pulse wave at its output. And we can adjust the frequency by changing the value of the feedback resistor through the potentiometer RB1. This kind of oscillator is used a lot in circuits that need a clock to work. We will learn later what a clock is, but for now, know that there are several circuits that need one, for example the microcontrollers and the microprocessors. Although for the latter we usually need a very precise clock, and therefore we need more sophisticated circuits than this one. An important thing to remember when using a Schmidt trigger inverter as oscillator is that when we use TTL logic for them, we are limited to feedback resistors of up to about 2K. Bigger resistors cause a voltage drop too high, and the circuit could not oscillate at all. And so, because of the relatively small resistance, when using TTL logic, we need to use big capacitors when we need a very long period of the output signal. If we instead use a CMOS logic, then we can use much bigger resistors and therefore much smaller capacitors. To avoid affecting the oscillator, I have added an extra inverter at the output of the oscillator itself, U1B, in the diagram. And yet another inverter, U1C, is used to be able to extract both the signal Q and its inverse, not Q, at the same time. Another inverter is used to pilot transistor Q1, which drives a red LED that allows us to see when the output changes state. The LED, in fact, is on when the output Q is high, and it is off otherwise. I have mounted this circuit on a breadboard, and I plan to leave it like that for a while, at least until we learn about flip-flops and how to make and use counters. Once we know what counters are, we will expand the functionality of this logic generator, we will assemble it on a perf board, and we will put the whole thing in a nice box. And that will be a nice addition to our small lab, and will allow us to experiment on digital circuits even more. Let's see now how this circuit is assembled on a breadboard and how it works. Here is the generator mounted on the breadboard. This is the SN74LS14, which is powered through pins 14 and 7. This is the LED, which is orange instead of red, but since they have approximately the same forward voltage, it works just fine for our scope. The LED is powered through this transistor, and here is the 2K potentiometer to modify the frequency of the oscillation. The potentiometer is of course in series with a 100 ohm resistor, which is visible here in the back. And this one is the capacitor connected to the input of the first Schmidt trigger inverter in the IC. This is the resistor on the base of the transistor, and this other one is the resistor that limits the current through the LED. I also added some test points to be able to connect the oscilloscope, so we will be able to see the actual signals emitted by this device. So, let me power up the circuit now and connect the probes, and let's look at the output signals with the help of the oscilloscope. Okay, the circuit is now powered up, and the oscilloscope probes are connected to both the Q and not Q outputs. And you can see the blinking LED that tells us that the circuit is working. Let's take a look at the oscilloscope now. As expected, the two outputs are one the inverse of the other. While one signal is at 1, the other is at 0, and vice versa. I have also set the potentiometer to have the maximum frequency, which according to the oscilloscope is 30 Hz, which is the one I was shooting for. I'm going to move the potentiometer now to go down with the frequency, and you can immediately see the effect on the oscilloscope. Here, now I am at 5 Hz. Let me change the horizontal scale of the oscilloscope so we can see more periods of the signal. Look at how good is the shape of the square wave, considering that we are creating an oscillator with a logic device. Let's go down again with the frequency, and let me also adjust the scale one more time. Okay, now we are at 3 Hz, and now we are at about 1 Hz, which is the minimum possible frequency with the components I have chosen. On the circuit itself, you can clearly see the LED blinking at the pace of 1 blink per second. And if I increase again the frequency, you can see the LED blinking faster and faster, until we cannot distinguish anymore the blinking because it has become too fast for our eye, although the oscilloscope clearly shows us that the circuit is working again at 30 Hz. It is always nice to have a circuit like this available in the lab, because it allows us to experiment with digital circuits without the need of using switches or jumpers to keep changing the inputs. The logic generator proves to be even more useful when the circuit we are working on has several inputs and we want to see what happens when we try all the possible combination of inputs. So far, this generator can only provide two signals, one the opposite of the other, but soon, once we learn about counters, we will be able to extend its functionality and have it provide several signals at once and in all possible combinations. So get ready for something new and exciting in the next episodes of the series, and to avoid missing some of the episodes, don't forget to subscribe to the channel and to click on the notification bell. See you in the next episode, and as usual, happy experiments!